Welcome everyone. Today we're going to be taking a look at the mole and the related applications, which are the molar mass and molarity of a substance or solution. This is really essential because in chemistry we care about the number of particles a lot. It really is fundamentally how chemical reactions work, yet we cannot simply envision this directly. We take other measurements and then we need to do some conversions to know what this value is. So again, we're going to look at how we track the number of particles in chemistry through this concept called the mole, as well as a couple of ways that we mathematically deal with getting to the mole in chemistry. The fundamental reason why we care about what we'll define as the mole so much is because the atoms in chemistry matters, the actual number of atoms that we're dealing with. And when we see this recipe for water, we say that it's 2 H2s plus 2 O2s, and this literally means 2 molecules of H2, 1 molecule of O2 is going to make 2 molecules of H2O. The atoms themselves rearrange, and it is the individual particles that do this, not like 1 gram of oxygen and 2 grams of hydrogen. So if we want to do this, we absolutely need to be able to track the number of atoms or compounds or molecules accurately in chemistry. This is how chemical reactions work, their rearrangements, and they deal with the actual atoms themselves. So how do we do this, given that what we're dealing with are these microscopic, tiny masses, and we probably don't want to deal with those numbers that are so small or so large so often? Well, we do this with what's called the mole. So the idea is that an atom is really small, and we really will not find it convenient to deal with large numbers in calculations. And so here is the number that we use, 6.02 times 10 to the 23, and we refer to this number as the mole. And I really want to draw the parallel to the fact that this is just a number, 6.022 times 10 to the 23. It's just like a dozen. You know, we don't track individual eggs in selling eggs because we track them by dozens. It's easier to deal with them as a package. This is exactly the same concept here with Avogadro's number and the mole. It's a massive number, and it's designed to make our calculations easier in a lot of ways. And really what's important to think about is that the mole is tracking the number of our atoms or our molecules or our ionic compounds or whatever. And so here's a formal definition you'll see in the book. It references carbon-12, and the idea is that we've learned about the atomic mass unit and how that relates to an atom. Well, if by dealing with the mole, we're going to relate that quantity to grams. So we'll see this in practice right here on the next slide, right? The concept of a mole is that we know that the atoms are different mass, right? Some atoms have higher atomic masses, and if we had a dozen of them, the mass would be higher. If we have a mole of them, the mass would be higher. And this is a depiction of a certain amount of each of these different substances that amount as a mole. And they all have different masses and therefore different apparent volumes and densities and things like that. So all of these have different masses because they're different sizes. I like to think of them as different fruits, right? If you have a dozen grapes or a dozen watermelons or a dozen oranges, they're all going to have very different masses and sizes because every one of those objects is a different size. The same is true for chemicals. When we're dealing with a mole, though, this is to say that, well, we still have the same number of these atoms. Just like if you had a mole of grapes, huge volume, right, but based on a grape, a mole of watermelons, much bigger, because that's all based on a much larger object. We need to consider the number, though, and that's where this idea of the mole comes in. Okay, the molar mass is the mass in grams of 1 mole of a substance. And again, you know, this is going to look familiar and feel familiar numerically in just a second, and that's by virtue of how we've defined a mole, why we chose this very specific number to be the number that we define as a mole. Because we see the following values, and we say, well, for copper, 63.55 atomic mass units per atom. This also means that 1 mole of copper is going to have a mass of 63.55 grams. So when we have this mass of a copper atom, it's also the gram mass of 1 mole. So it's meant to be convenient as far as the value of this number, even though these units are actually very different. They mean pretty different things. That's because of the mole, but it does allow for some nice consistency through where we look up masses. This is the average atomic mass, and this is the molar mass. And this is very easy to mix up and think are the exact same thing, and you'll even get away with that for a while, I would say. But remember that the molar mass is the same in number, but it refers to 1 gram and 1 mole of a species. And maybe just pause here and think about the following question. Where did we get these values, right? For copper, 63.55, where did this number come from? Go ahead and pause and let me know what you think. All right, these values, periodic table, right? This is the average atomic mass off the periodic table, and we see that we can get the molar mass, the grams per mole, off of this same value. Okay, so here's another activity. I recommend you go ahead and pause here as well. Now we're dealing with compounds, not just individual atoms, but the idea is still the same, right? That we're kind of gluing these things together, and when we look at carbon dioxide, well, if we are to glue 2 grapes to a watermelon, so to speak, 1 dozen of those is going to be 2 dozen grapes and 1 dozen watermelons, right? So think about that. This is a good review of nomenclature as well. Pause here and see if you can get the correct molar masses. All right, hopefully you're able to pause and take a look at this. Here are the molar masses. If you're just a little bit off, that can be from using different periodic tables, so no big deal, but it really should be, you know, within 1/100th or 1/10th of a gram per mole off, not too much more than that, to ensure that you've gotten it correct. Okay, the molar mass can be used as a conversion, and this is perhaps the most important mathematical treatment point here with the molar mass. We've looked at dimensional analysis, we've worked through that very thoroughly, and when we're dealing with the molar mass, this is because it relates carbons, moles, to carbons, grams, for instance. It relates moles of a species to grams of a species. And therefore, we can express it in the following ways. We can express it 1 mole of carbon per 12 grams of carbon, 12.01 grams per 1 mole. This is the molar mass, 12.011 grams per mole. We've seen this before with a variety of conversions, and how to use these will show up again and again and again, so if this looks unfamiliar, definitely worth reviewing your dimensional analysis. Okay, with this in mind, let's pause again and try to do these conversion questions. Moles in 50 grams, mass of a certain amount of moles. All right, hopefully you're able to deal with these. Again, we always want to start with what we know specific to the problem, and it's kind of given to us here. For the first problem, we start with 50 grams. We want to arrange the molar mass so grams cancel, and we end up with moles of carbon. If we're starting with moles, we start with moles, and we arrange the molar mass so moles is on the bottom, canceling out moles and getting grams. This conversion between grams and moles is really essential because as we get towards reactions and knowing how chemistry kind of works a bit more, we almost always need to deal with that in terms of something dealing with the number, meaning moles. Furthermore, we make solutions. So molar mass, this is really useful for dealing with solids where we have a mass that's straightforward and easy to measure. But again, the uniting concept is moles, and we can deliver moles of a chemical species, meaning the number, a variety of ways. And another one of those ways is through a solution. So a solution is a homogeneous mixture with a uniform composition. We have 2 parts, a solute that's getting dissolved into something else, generally present in the smaller amount, and the solvent that does the dissolving. And here in chemistry 1, general chemistry, we almost always use aqueous solution as the solvent. So water is the solvent for an aqueous solution. If we are dealing with solutions, well, the solute is really what we're probably considering the moles of. And if we're doing that, it's really important to know the concentration of that solution, how much solute is present for a given amount of solution. If you have a sugar solution and you just have 2 sugar molecules in a bathtub of water, that's very different from if you have, you know, a giant scoop of sugar per 1 small cup of water, for instance, right? The richness, the sweetness of the solution matters because that's what we're delivering to chemical reactions very likely. And we track this through the molarity, which we define as capital M, moles of solute per liters of solution. Okay, so with this in mind, moles of solute per liters of solution, let's take a look at the following question. What is the molarity, again a single number that expresses the moles of solute per liters of solution with units that will be capital M, of the following combination? Go ahead and pause here and I'll show you my answer. Alright, so now that we've looked at this, we see that what we really need to do is we need to convert each of these to their correct unit within molarity. So the grams of H2S, this is a solute, this is 0.662 moles of H2S, which we do using the molar mass, grams to moles. And finally, we convert the 250 milliliters to liters, that's 0.250 liters of solution, and we divide the two, we get the molarity. We express it with units of capital M, which literally means moles of solute per liters of solution, and H2S gets square brackets to indicate that this is the molar concentration of H2S. Very important vocabulary notes to remember for interpreting problems as you go. Again, this is a universal notation, it's not just a decoration, and when we read this, we should read bracket H2S as the molar concentration of H2S. Okay, go ahead and pause here again and try this one. How many moles of NaOH are in this amount of this molarity? And this is really where things come into more relevance, because so often in chemistry we deal with chemicals in aqueous solution or in some kind of solution, and we need to know how many moles we're bringing when we use a certain amount of a certain sweetness, right? If we have Coca-Cola and you have one sip of Coca-Cola, we can figure out how many grams of sugar are in that one sip based on how sweet is the Coca-Cola and how big is that sip. If we drink a 2 liter, then we can know how much total sugar did we drink based on the fact that it's 2 liters and the sweetness of Coca-Cola. So here, right, the size is the 1.85 liters, the sweetness is 0.25 molar, and we can figure out how much total NaOH we brought. Alright, hopefully you've been able to work through this one. 0.463 moles. We do this again through dimensional analysis, but we can also see through the following formula. Again, this capital M means moles per liter, so calculating in this way, liters cancels with liters, leaving us just with moles. To wrap things up, moles is absolutely instrumental. This is the number of a chemical species. It's just a number. Like a dozen is always 12, 1 mole is always this number. And so, again, if we know the number of moles, we know the number of particles, we know the amount of stuff that's around, not in terms of grams, but in terms of actual number, which is really, really essential to know in chemistry. And we looked at 2 different ways that we calculate moles. First, from grams of a species using the molar mass, absolutely instrumental. Grams is measured directly in a laboratory, whereas moles is not, and being really fluent with this idea that if we know the grams, we know how many actual particles are there, as long as we know what the species is. That is the molar mass. That is going to move forward in chemistry forever. The volume of a solution we can get from the molarity, and knowing how we track concentration using a unit like molarity, and how to get moles out of a certain sample of a certain solution is also absolutely essential.